Okay, welcome back, and we will finally have our first physics lecture, and it will be on the accelerator that you will do on Friday, and not only this accelerator, but also how we are planning to upgrade it to 22 GeV, the electron beams energy. So Yves Roblin will tell you all about this. He started as a nuclear physicist, like all of us here, then switched to accelerator physics. So he's a perfect person to explain to us all these things. Thank you.
Right. Can you hear me? Yeah. Thank you. So here at Jefferson Lab, we have several accelerators. I'm going to discuss mainly in this first lecture the electron accelerator that we call CEBAF at Jefferson Lab, and then I will discuss how we are planning to upgrade it to reach high energy. Right now, with this accelerator, can reach up to 12 GeV in all D and 11 GeV A, B, and C. We have 4 experimental holes, and there is a huge body of physics you can access if you go from 11 to 22. Patricia will discuss that tomorrow in a talk specific to the physics of the 22 GeV. So I won't mention that. I will just show you an overview of the accelerator, how we upgraded to 22. In my second lecture, after the break, I will discuss the other projects that we are considering here at JLab for the future of JLab, which is providing this accelerator with a positron source. It's also very interesting from a physics point of view, and I will show you the physics behind that. What kind of physics program you can reach if on top of the electron beam, you also have a positron beam up to 11 GeV. And I will show you how we build the machine for that. All those projects are currently happening in terms of all the R&D is going on to figure out how to do that. At the same time, there is a very active community of nuclear scientists who are proposing new experiments. They are going in front of the pack, and we already have a good number of experiments that are ready to go should we produce that positron beam and that 22 GeV CEBAF. So Jefferson Lab, where you're standing here, is one of the, I think it's 18, Department of Energy labs. 17, yeah, I never know because changes. This slide is from 2 years ago. We have one more core competency I will mention in a second, but we specialize in nuclear physics research, obviously, right? We have an electron accelerator. We also are leaders in SRF technology. This accelerator is using superconducting RF to accelerate the beam. In order to do that, you had obviously to build superconducting RF cavities, and this is where most of the research happened and the development, to such an extent that we are now building some for other labs, right? We still have a leading role in SRF technology. Another area that is very important to CEBAF, and that's one. I will use CEBAF when I talk about the accelerator, Jefferson Lab when I talk about the lab in general. Another area that's very important to the CEBAF machine is we have a polarized electron source. Not only are we producing high duty cycle, high current electron, but they also are polarized up to 85% or so. This is hard to achieve, and for many years, people were stuck at 40 or 50%. JLab and the scientists in the injector group were instrumental in figuring out how you do that and to reach high polarization, still delivering high current with a good lifetime. And we still are world leader in this. We usually will be consulted for other labs that if they want polarized electron source, electron guns. Obviously, to run superconducting RF, you need cryogenics. So that's another outcome of building up the lab in the early 90s, late 80s. is that we had to develop a cryogenic solution to be able to cool all those, there's 400, a little over 200 per linac cavities. They all are running at 2 Kelvin with liquid helium. And so we produce the helium there. We have a cryo plant. And when in Europe at CERN, when lab shut down before LHC started, we were at one moment the biggest in the world cryo plant. It's a significant, we upgraded it from 6 to 12 GeV. So this machine initially was built for 4 GeVs and quickly upgraded to 6. We did a lot of physics for many years, groundbreaking physics at a 6 GeV beam. And in 2013, we upgraded this machine to 12 GeV, double the energy that was done by upgrading the SRF with cavities that had a stronger accelerating gradient. But that implied that we needed to upgrade the cryogenic plant. We had to build an extra one. So now we have two different cryo loop, one for the north, one for the south linac. So that doubled again, in 2013. We also have a group which I belong to of accelerator physics group and diagnostic development to transport, beams along the machine. You have to deal with things called beam dynamics. I always joke that it's simple. It's 19th century physics, right? It's maxwell equation, right? You transport a beam by bending it with field or accelerating it with longitudinal field. In practice is not that simple. It's a mix of technology and physics on collective effect, all those things, right? So we have a group that does that. One thing that's not on this slide is we also have very strong presence in computational physics, in particular, lattice QCD started there. There is a huge number of theorists here who are working on doing lattice calculations. More recently, we got awarded a significant chunk of money to set up a high-performance data facility center for the entire DOE. So it's going to be built. They're going, I think, to add a wing to that building, and it's a big project. And the idea is nowadays modern experiment. If you haven't noticed, you will see in your work, right? That they generate terabytes of data per some of them, per day or even per second. Gigantic amount of data, right? And this data has to be, stored and processed and analyzed. And so you need supercomputers and you need facilities to move it around. Like if you work here, but you are collaborating with colleagues in Europe, you may want to transfer, access the data from CERN here and vice versa. So all those things are being part of upgrades that the DOE is doing in terms of, high-performance data centers. This was from the 2022 public information, the annual plan of the lab. This number is no longer true. It's way more than 180 million. It's probably like 250,000 or something because of all the extra things we're doing. One thing I want to point out, so the campus is about 170 acres. So it has the CEBAF accelerator. It has where we are standing here. It has test facilities, many things. Lots of users, we are a user facility, right? So people come to do experiment. Full-time employee, it's a mix of scientists, technicians, engineers, across a lot of different disciplines to run this accelerator. You need electrical engineer, you need, people of all sorts of specialties, right? Not just scientists, right? This lab is a center of excellence for nuclear physics. As a matter of fact, we produce roughly a third of all the PhD in the US come from people like you guys who come here, do experiment, do their PhD experiment, take their data here, right? And get their PhD, or if you're in theory, be in the theory group. But that's about a third of the US PhD come from here, or have in the past for many decades. So this accelerator, you saw the picture here. So, North Linac, South Linac, all A, all B, and all C here, and then all these on the other end. So it's obviously underground, right? For obvious reason, you want to, to protect from prompt radiation, right? So the best way to do that is you bury the thing. At CERN, all their machines, they are buried underground as well, but they had to dig up tunnels. They had to use huge tunneling device. Here, we had, since it doesn't have to be very deep, because it's only 20 GeV at most, we had to bury it 30 feet. So when people build it, they instead dug a big trench, put some concrete tunnel, and then cover it. That's called cut and cover. This is so this accelerator is sitting on some geological formation called the Electron formation. Why is it interesting? Well, because it's interesting, but also in the experimental holes, we are below sea level, right? So if you go down in the accelerator, down in the tunnel, there is you will see painted on the wall, there is a line that shows little fish and everything that shows sea level. We are below sea level, which means that some of the experimental holes we are pumping constantly so that they don't end up flooded because we are way below sea level. This is a schematic of what that accelerator looks like in 2D. So the way this works is we have, and I will discuss it in more detail in my second lecture, an electron gun. So what is that? That's where you have to generate the electron somewhere to start with, and then accelerate them and send them to the experimental hole. So the way you generate polarized electron is you have lasers, circularly polarized lasers, and you shine them on a cathode. That cathode is a strained gallium arsenide currently. It's a semiconductor. And the way this works is if you bring energy with your photon, you will pull electron because you will bring more energy than the work function, it's called. So you will pull electron out of the semiconductor because it's doped. So it's the valence band is small. So you pull electron, and the process is such that the helicity will transfer. The circular polarization of the photon will transfer into longitudinal polarization of the electron that you extract. Okay, so you get longitudinally polarized electron. What do I mean by polarization? It's a weighted average of the orientation of the spin of all the particles in the bunch. So we refer that preferential direction as polarization vector, right? You can look at it in, along the beam or transverse to the beam. This is observable, and the quantity that is critical when you do physics experiment, because depending on what you're trying to probe, we'll discuss in the second lecture GPDs, for example, you want sometime a transversely polarized beam or longitudinally polarized beam and so on. So you make that beam by shining lasers. You have one laser per hole. We have 1, 2, 3. Let's ignore D for a second. Not that they're not important, it's critical, but to simplify my description is you have one laser per hole, so we have 4 lasers, and you want each laser will extract electrons for each of the hole. And then those electrons, once they are extracted, they are picked up by high voltage. So initially, our polarized gun was 130 kilovolt. We have since designed guns at all the way to 350. Right now, 2 weeks ago, I think it was 2 weeks ago, we stopped running. We were running all winter. We're going to restart running the machine, I think in November. Right now, we're in maintenance activities. So when we were running a couple of weeks ago, this was 140 kilovolt. We are planning to upgrade it to 200 kilovolt this fall. So this high voltage plates, just pick up your electron, accelerate them, and then it's subsequently accelerated with a warm radio frequency resonant structure manipulated in this part of the machine. So this is laying on the floor horizontally. Of course, it's a schematic. And in here, there's lots of stuff, magnets, RF systems that we use to condition. And I will show you an example in a second of how you make beam bunch. Condition the beam, diagnose the beam, check spectrometers, like you guys have since experimental hole, to check, for example, the energy spread of the beams, the momentum or energy of the beam. So in this part of the machine, you have to pay attention whether you are talking about momentum or kinetic energy, because it's significantly different. Of course, as you keep accelerating, it's no longer as much of an issue because it's relativistic, right? But when you are generating at 140 kV, you have to pay attention to momentum versus. versus energy. Once we have that beam generated and accelerated, there is some SRF here. The beam gets to the main machine. So we have two accelerators, one here, one here. We call those north and south LINAC because that's the way they're oriented. This is north here, south is here. And these accelerators are a collection of cavities that are grouped inside big tanks. Each tank is, a cryo module that's filled with helium. And you come in with a beam, for example, at 123 MeV, and that you make it such that you synchronize your resonance system, your RF cavities, with the phase of the laser, with the phase of the bunch, so that your bunch arrive on top of the crest of the RF wave. And so it's accelerated, you impart kinetic energy to your electrons, right? So by the time your electron gets to the end of this LINAC, it's at 123 plus 1090. We can adjust this acceleration on that one by plus or minus a factor of 2. This is the top end, 1090, to get 12 GeV in all D. But depending on the experiment, sometimes we want to accelerate less. Some of the reason I will explain having to do, for example, with spin precession. Sometimes it's because of the kinematics of the experiment. So you accelerate your beam, it gets here and here. So this part, the recirculation arc, it's vertical. There is a picture of it as you walked in, in the E = mc square thing as you walked in, there is a picture on the wall of those return arcs. So those are magnets, they are vertical. So the first time you come in, the beam, there is a big magnet here, dipole, and as you know, dipoles, they bend, they have a magnetic field. So in that case, it has a downward magnetic field, and it will bend the beam vertically. No, not downward, sideward, but it will bend the beam vertically. And since it's designed such that the first time when the beam is at 1.2, it will land in the arc that's on top, which is arc 1, which is the low energy arc. So each of those recirculation arcs, whose goal is to transport the beam back into the next LINAC, that's what they do, is unique to one particular energy, right? Once you decide what you want to have in the injector and what the acceleration is there, this fixes the energy in the arc. So your beam gets in there, is transported. So there is a collection of magnets called spreader magnets that are vertical magnets that are designed, again, to transport the beam and distribute it on the various arcs, depending, and it works simply by the fact that some of these magnets are common, they only have one set point. So the next time you come around, now the beam is higher energy, like instead of 1.2, it's 3.3. It's bent a third as less for the same set point in the magnet. So those magnets are not pulse magnet, right? They have a field set point, a static one. It lands in the next arc, which is below for the next pass, right? 3.3, and so on. So that's how it works. It's symmetric on that side and that side. So basically, you take the beams, you get them up into their recirculation arc, then you get them back down to distribute them into the next LINAC. That's how this machine works. You can go up to 5 times through the machine, and each time you do a pass, what we call a pass is a full turn, right? You pick up, acceleration, and you keep doing that until you end up eventually at pass 5. So you go 5 times around, and the beam then it gets sent to either A, B, and C depending on on what you want to do and which experiment is running what. If you do not want 11 GeV, if you want less, we can peel off the beams at a lower pass. So you can decide, for example, you're in OLE and you want to do an experiment that only requires the first pass, 2.2 GeV, let's say some hypernuclear experiment or something. You simply ask, accelerator scientists, and the operation groups, and they will operate those system, RF separators, and I will discuss that later, to peel off the beams that you want to send from the main machine that you want to send to the hole, and the other 2 beam or 3 beam, if all D is running, will be kicked in the opposite direction and be recirculated in the main machine. So at any pass, you can decide you can only peel off one beam. So the way the machine is constructed, only pass 5 allows you to have 3 beams together. So if you have, have more than one experiment running, which is what we try to do at JLab, right? We try to maximize the use of the beam, right? So we schedule more than one experiment at once, obviously. So you can have an experiment in OLA, for example, that's taking beam at pass 1. The whole B people may want pass 5, and the whole C people may want pass 5, which is fine. Pass 5, you can have up to 3. For the other pass, the scheduling has to be such that only one, experiment can take that pass, right? So scheduling and all that stuff is handled separately from gauging whether an experiment is worth doing, which is what the program advisory committee is doing. It's right now actually happening. Experiments are proposed, right? And then there is a group of your peers that, or the scientists that evaluate whether those proposals are meritorious, right? Whether they will advance the field. And if they do, then they are approved and eventually then scheduled to be run in the machine, right? So the scheduling committee then will schedule those experiments. So that just summarizes what I just said for the injector. There is a bunch of things in that injector. So at what frequency is that done? Those lasers, they are pulsed at 499 megahertz. That's why it's a high duty cycle machine. If it's all D, 249.5, if all D is running and you have somebody at pass 5 for technical reason, you need that. But other than that, now we can adjust this, by the way. So why is that interesting to adjust? It's because if you reduce this, you get more bunch charge. Some experiments, like years ago, G0, where we're doing a specific experiment, want more bunch charge. So then you reduce that number. We can run. There is another 1K long that has been considered in a few years. That requires a specific bunch structure. But in general, it's 499 megahertz. And the RF cavities, they run at 3 times that, 1.5 gigahertz. So this is a subharmonic. So it all works in terms of synchronization. We have a bunch of stuff. I'm not going to describe, the beam dynamics of all of that, but basically we can condition the beam longitudinally, transversally for a specific envelope, a specific bunch length, a specific energy spread, which is another parameter that's important for physics, right? For some experiment, you want tight energy spread. If you are trying to do experiments, like hypernuclear experiment, for example. You then can diagnose the beam, accelerate it further down, and then send it to the rest of the machine. So why CW, by the way? So there are obvious reasons to use so CW, continuous wave accelerator. And this means the beam is high duty cycle. Well, first, the technology, the SRF cavities won't melt, which is a good thing, when you push a lot of power through them. Whereas warm RFs, there is an inherent limitation. So SLAC, for example, has the initial SLAC Linux at warm RF. So it's pulse. It's a pulse machine. It's like 120 hertz. Here, we just told you 500 megahertz, right? And it's constantly on, those RFs. They don't turn on off, unlike warm RF. And you can only do that if it's superconducting. This is why you don't have thermal effect, and the thing doesn't melt. So that's one reason why we use high frequency, high duty factor. Another outcome of that is that if you have more bunch for a given second, then you have less bunch charge in each bunch, right? If you distribute, the current is, of course, charge time, right? So if you distribute your charge in more bunch, you have less per bunch, which means that you have less pileup in your detectors, right? So that's another big advantage of CEBAF. Also, this allows you to measure very small cross sections. Because of that reason, it's clean. You can make narrow coincidence windows. You have less accidentals. CEBAF allowed experiment to reach, high luminosities that on fixed target, and in all B, it's on It's for pi detectors and all this, but in the overall, to reach very high luminosity that we couldn't reach anywhere else. And that was one of the main advantage. The beam structure, so when we tune this machine, we also don't want to melt the beam pipe. So the beam, if we are sending high current beam, it can be near megawatt, right? You multiply microamps by GeV, you get a kilowatts, right? So 10 microamps at 11 GeV is 110 kilowatt. If you are sending, if a hole wants 70 microamps, 700 kilowatts, that's a lot of power. And for the CW beam, the continuous beam, you can't really tune the machine. So in theory, you would think, we calculate all the set points. We have models, right, that knows what you should put in those magnets and those cavities to transport the beam as needed. There's about 500,000 set points in this machine that we monitor and set. It's obviously done by computers, right? But the odds that everything is working at once is nearly zero. So there's always something that's off nominal, not working. So you have to compensate for it. So we have to tune, right? And you don't do that with a high power beam because you would destroy everything. So it's done with a special mode where you only have 1.5% duty cycle. You only put budge into only a small fraction of the every 60 hertz of the entire second, right? So that's what we use when we tune the machine. So to control the beam current, so as I said, you shine a laser on the cathode, you produce electron, then they get to that thing called a shopping system. And so you have your bunch coming in, and your idea area is you want to be able to independently control the current for A, B, and C, and D. And you do that by, you use transverse RF kickers that takes your beam, so they're at 500 megahertz as well, and you have an X and a Y kicker, and sinusoidal forms. Of course, you will describe a circle if you do that, right? So you kick X and Y, and you have your beam landing on a circle onto which, I will show you a picture, it's a copper plate with actual mechanical device to restrict the beam and control the intensity. You dump electron on this. So you adjust that shopping, you synchronize the phase of each laser with that of this, such that on average, every 500 megahertz, you will see a beam. They are 120 degrees apart in phase, and then you have something like that. That's what it looks like, right? It's a copper thing. So A, B, or B, C, A, D, and we have a viewer where you can actually see. So those are real beam, right? B, C, A, and you use that to not shown in this picture is on the back of that thing, there is some mechanical device called slits that you can insert. So they are V-shaped that you can insert up or down to restrict the amount of electrons that are coming out. So that's how you control the beam intensity. We can deliver nanoamps. For example, in all B, typically they run, or all D, they run with a few nanoamps, like 50 nanoamps, sometimes less. We can deliver microamps. For the high current holes like A and C, up to the capacity of their beam dump, which is a megawatt, where you see, and the capacity of the machine, which you can't have more than 900 megawatt in the machine together with all beam. All right, so once the beam is out of the injector, I guess since that's what I was discussing earlier, see those big tanks are where the cavities are with the helium in it. So in between those modules, we have quadruples, which basically provide magnetic field, allowing you to compose the beam envelope, make a periodic structure. At first order, if you write the equation of motion for these beams, it's like an harmonic oscillator. In the quadrupoles, they play the role of springs, right? So you adjust the quadrupoles to make a periodic structure. And this shows you the beam envelope. So along the linac on the first pass, the beam goes like that in X and in Y, it's symmetric. But since you're accelerating, when you accelerate because of the Lorentz boost, the transverse momentum shrinks, which means that in terms of those are factored out, it's called the beta function, which is what the periodic system looks like, but under acceleration, it shrinks. It's useful for, well, it's useful, it's what it is, you can't beat it, it's there, right, because of Lorentz boost, but it's also used in a useful way for parity experiments that are interested in having suppression of beam LST correlated beam asymmetry. We are doing experiments at JLab. Many of them, it's actually a big part of the physics program. Experiments that are using LST, like you flip the LST of the electron beam and then you measure asymmetries in the hole, but you want to measure the physics asymmetry. You don't want to measure the asymmetry coming from the beam. And one of the ways you minimize that is you make sure your machine is well tuned, so it shrinks the beam optimally. Yeah, as I said, there's 418 cavities in CEBAF. Here, I just want to mention that they are of different generation, meaning we have old cavities that are C20. They generate 20 MeV of kinetic energy acceleration for 8 cavities. Then we had newer models, C50, 50 MeV, you guess it, and C100, which is what we added to go from 6 to 12 GeV. Those last 5 zones do as much as the first 20. That's how much the technology, SRF technology has improved over the years, right? So we have now we have more, we are constantly adding some more of this to have more headroom. Right now, during the summer dawn, we're adding 3 more of the C75 and C100 type. I might flip that. So that's just to show you I was telling you earlier that you take the beam out of the LINAC and you put them in the arcs. This is what it looks like in terms of magnets. So there is one common magnet that will bend the first time the beam here, then the second time the beam here, and so on, right? As the beam gets more energy, it's bend less, so it lands into lower arc. And the equivalent recombiner on the other side. What we call west is on the other on the left on my picture and east. So there is a bunch of properties, but it's messy, right? It's messy in terms of occupancy. Lots of magnets. You have to adjust those just right so that the beam goes where you want it to go. This is what those recirculation act arc looks like. So that's the west side. So that's arc 2, arc 4, arc 6, arc 8, and the new arc for D, arc 10, which is for D, you go one more time through the North LINAC to go from 11 to 12. So you have an extra arc. That's what we did in 2013. We added. So those are 4-meter dipole. So we have an assortment of 1, 2, 3, and 4-meter dipole. And this is what quadrupole looks like. The implication, by the way, I should mention of going from 6 to 12 GeV is that we have synchrotron radiation to contend with. Since the band radius, the tunnel radius is fixed, right? The higher energy you try to push, the more issues you have with the fact that if you bend an electron, it will emit synchrotron radiation, and this will increase phase space emittance of your beam, and this will also increase the energy spread, which is, if you're trying to do an experiment that requires a nearly monochromatic beam, it's not ideal, right? So one way to combat that is have longer magnets and also more quadrupoles, but we are reaching I will show you that for the 22 GeV CEBAF, we use a completely different strategy. The first 2 arcs are different from the others. For technical reasons, we use those as spectrometers. So they have what's called high dispersion, kind of like a spectrometer in the hole. We have parts of the arcs in between dipoles that are very sensitive to energy deviation. And we have measurement device, beam position monitors that we read out. And then from there, you fit and you calculate how much off your beam is in terms of energy. And then we have lock-in system, locks, right, that take all that information and adjust the cavity on the fly to keep the beam on energy. It's important when to have the energy constant when you do an experiment. So the holes also have device to measure the average energy in their beam. They regularly, so can normalize your data. We'll ask us to do an energy measurement. But in the meanwhile, we have to keep it constant in between measurements, and this is what we use. Extract the beam, as I discussed that earlier, it's done with SRF transverse. So cavities can be configured either to accelerate or to kick the beam. So those are transverse kickers at 500 megahertz, and they allow you to kick the beam. You can set the phase of the beam such that one is kicked to the left and the two other on your wave are kicked to the right, and then they go back through more magnets and keep going, whereas the others are extracted. So as I said, it has to do with where you place it. So see, one goes to the left, these other two. So this one will be kicked minus 200 microradian, which is the number we use. The other two plus 100. And that's how we proceed. It's all a game of timing, right? Adjusting things and path lengths and that's how this works. The machine, by the way, shrinks and expands with temperature variation significantly enough that we also have to adjust that by using some of the system doglegs, where you make the beam go longer or shorter path to compensate, because you want the phase, you want when you arrive in the next linac to be in phase with the RF, right, as you keep recirculating. So there is a timing issue, and it's not a small effect. It can be, millimeters, and millimeters is huge for an electron, especially an electron that's seeing a resonance system that's 1.5 gigahertz. It's 20 centimeter wavelengths. This is what it looks. Operations, when they extract the beam, we have various viewers in the machine, where the electron in a special mode where they are low current. They excite those screens. Those screens are fluorescent, and they give you position. And so you use that to set up the machine. This is what it looks. So see, the bunch are at 500 megahertz. The accelerator is accelerating at 3 times that, so it's subharmonic. If you want to accelerate, you want to extract, you have a separator cavity, you turn it on, and you adjust the phase so that you end up in that situation. And if in that situation for the and then for the vertical separator at the end at pass 5, and see, you can have a beam that goes straight, all B goes straight, all A can go up, and then it's put in another magnet, which then, depending, that has 3 holes, one on top, one in the middle, one in the bottom. All B is in the middle, it has no bend. All A is on top, and it's bent to the right, and all C, the bottom is bent to the left. So that's how you send the beam at pass 5 to separate all. Again, some RF manipulations, kickers, followed by magnets. So this is the current performance of the 12 GeV beam at CEBAF. We have a multiplicity of 4, meaning we can send beam to 4 at once, A, B, C, and D. We can reach, as I said, either 11 or 12. All D is 12, 100% duty factor. We can pull out of the gun much more than the machine can sustain at 12 GeV, right? Because we have power limitation in the dump and stuff. But if you are running at a lower pass, you can ask for more current. In the past, we ran experiments in all seat 180 microamp, like G0. Whether it's polarized or not, no problem. We can run high current. And with high polarization, in my next talk, I will discuss what the kind of performance we can expect for positron and why it's so much less because of the way we produce the positron. But other than that, it's the same idea, same frequency. It will be a CW beam, but less intensity, will be polarized. So this is an overview of the CEBAF machine, and now in a second I'm going to discuss our project to make it 22 GeV. So we are going to start with that exact machine I just discussed and make a few adjustments. So this project has been under studies for several years already. It's a collaboration of various labs, not just JLab, but we have colleagues from Brookhaven or Creighton, Cornell University, who are collaborating with us. So how do you make a beam at twice the energy? Well, you could think, well, that's easy. All I have to do is put more RF cavities, right? I was telling you earlier that we have old cryo modules that only accelerate 20 MeV. You just upgrade them to 100. So technically, you could do that, but then you run into several problems. First is horribly expensive. SRF is very expensive. Second, you won't have enough cryo capacity, right? You will have to update the cryogenics. Third, you will have to update the magnet because now they have to bend, So many issues. Instead, the other idea is to do what we already do, which is just recirculate twice as much, right? Instead of 5 pass, if you do 10 pass, obviously you'll have twice the energy. The problem for that is you would have to build new arcs, right? Dig, because the bottom arc is already on the ground. So now you have to dig, right? And put more arcs below. You can't really, it's not really realistic to do that. So people came up with a third technology, which is very nifty. It has been tested elsewhere. It's called FFA, which is a fixed field, fixed field cells that are made of combined function magnet that are designed such that you can now transport beams of several energy in one single structure. Here in the regular CEBAF, as I told you, the circulation arc only take one energy. It can take several beams, A, B, C, D, but only one energy. FFA arcs, return arcs, they allow you to stack, like a factor of 2 in energy. So the plan is to remove the last 2 arcs, arc 9 and arc 10, and replace them with those FFA arcs. We also will have to build a new injector because we have to inject at higher energy, and we recirculate more, and then we get 22 GeV. Another interesting thing is those FFA arcs, they are made of permanent magnet, no power needed. It's incredible, but they are, there are materials that are such that, they produce Tesla strange field permanent magnet. So how does that work? As I said, we're going to accelerate the beam with a regular system until we then reach this FFA, and then the subsequent acceleration, they're all going to sit in the same FFA cell. We make the whole arc out of 75 of those cells. So it's a BD magnet, BF magnet. So basically, it's a dipole with defocusing field, and then a dipole with focusing field, and with large aperture. So here it's plus or minus 3 centimeters. And you can stack all those beams from 11 to 22 GeV in that single structure. It has a number of interesting properties. It's, for example, it's not very dispersive. So dispersion is a fact that in a regular dipole, if you send a beam with a different momentum, of course, it will be deflected proportionally to that. This thing is designed such that there is very low dispersion. This allows you to have low effect of synchrotron radiation, meaning you won't have a lot of emittance growth. You won't have a lot of energy spread generated from the synchrotron radiation, and you are able also to stack all those different energy. This is what those little magnets looks like. It's built out of separate smaller ones, and you can calculate the structure that they should have to produce a focusing or defocusing magnet to fill that up pretty strong, like 40 Tesla meters. That's already what we use at CEBAF, typically tens of Tesla per meter. But those are permanent magnets. This is, we build a prototype, and we are producing 1.5 Tesla for this permanent magnet. One of my colleagues who is working on this was telling me it's pretty funny. So he got a shipment of those, right? So they come in, you have to assemble them. and he wasn't too careful, and suddenly two of those things stick together. Well, it took a while to unstick them, right? Because it's extremely strong field. You have to be careful when you manipulate those things. So that has been tested. This is a simulation. Here's all 6 energies, all the beam. That's how they, by one of our colleagues at Brookhaven. So this calculates all beam dynamics, right, with this system. And basically, we know we can transport all those beams happily through the system. They're all different energy by a factor of 2. On top of that, we will have to build some more complicated device to then merge all those beams. They are transported in the arc, and then you have to merge them back put them in the LINAC to accelerate them, and then unmerge them, and so on. So it's called a merger, and it's a pretty complicated optical device that's currently being designed and simulated. So how do we? So for all of that to work, by the way, you can't use the regular 123 MeV out of the regular injector, because the ratio between the injected energy and the final pass is too large, and that causes a beam dynamics problem of focusing. So instead, we need to inject 650 MeV, and for that, we're going to make a new injector in the LERF, which is a separate building. There used to be another accelerator there called the free electron laser, the FEL. Now it's not in use other than for testing SRF cavities. And we're going to build a recirculating injector there that can produce 650. It has a good synergy with the positron project that you will see later. For the positron project, we also are using the LERF, but to make a beam to hit a target, a tungsten target, to produce a positron by Bremsstrahlung and then accelerate them, it's the same. And we can reuse a lot of the stuff we are building for the positron project in order to do the 22 GeV CEBAF. So there are various combinations you can do. You start with 10 MeV electron. We are building that gun. I will show you in the next talk to do that. One of the challenges of this project is to be able to keep the beam contained in terms of beam envelope as you keep accelerating, because as you keep accelerating, the gradient in the LINAC becomes smaller and smaller, because our quadrupoles, they are not pulsing, right, in the LINACs. So for a given set point, as you increase the momentum of the beam sees less and less field. Well, it sees the same field, but it has less and less effect on it, right? And so you have to build alternate system like triplet cells. So we're planning to do that. This is what the switch yard will look compared to what we had before, the spread-on recombiner. Another bunch of magnets everywhere. So that's currently been designed and simulated. It's interesting because all those projects is always a combination of technology, beam dynamics, physics, and you have to balance all of those things together. You may have a perfect solution on paper that's, beautiful, right? Mathematically, just you can't build it. So you often have to go back and forth and compromise certain parameters to be able to, to do that. Here, I just want to mention that, interestingly enough, because of this FFA system, the synchrotron radiation effect that usually brings you extra, emittance growth and extra energy spread will not be too bad at 22 GeV, because those FFA arc reduces it, so it's manageable. So this project is currently ongoing. As I said, I may have the timeline next, or maybe it's in the next talk, that shows you when all of that is going to happen. Well, it's in the next talk. But the plan is we are building it as we are. So the immediate future of JLab, of course, we're doing the molar experiment, which is the weak mixing sine squared theta W. We are measuring that. It's a flagship experiment in Orlais. It's starting next year. That's the immediate future. Meanwhile, we are designing new detectors for Orlais called SOLID for semi-inclusive experiment. We are working on this and the positron project, and the timeline is we want to be able to, we will do the SOLID program first, SDIS first, and then by the time we get to 2035, so all that stuff I'm discussing, you guys will have to deal with it because many people like me will be retired, right, or emeritus or something, or you know, the timeline in physics, you always have to see far ahead, right? Because to build those machines take years and decades and money and billions, and you have to take into account not just the physics, but the politics of it, right? Can you get it funded, right? Which is not always easy, right? It's not just true in the US, it's true everywhere, right? And those are big machines. I mean, this is small compared to CERN, but still, it's a project, right? So you plan ahead, you have to build your physics case. Once you have a good physics case, like, you know, it's worth investing that money to do that physics because it's groundbreaking. Then you have to design the machine, build it. So the positron would be running between 2035, 2038. After that, we'll stop, finish building the high energy CEBAF, the 22 GeV CEBAFs, and we'll do all those full experiment at 22 GeV. Patricia will tell you about that tomorrow, the physics you can reach at 22 GeV that you can't reach at 11. The positron will be able to run up to 11 GeV for a simple reason that beyond that, since we're using permanent magnet, we can't flip their polarities, so you wouldn't be able to transport the positons that have the wrong sign compared to the electron. Up to 11 GeV, obviously you can because we have power supplies that we can flip the polarity, right? Which is what I will discuss in the next talk after we have a break, how you make positron. And basically, you know, obviously you have to flip the sign of every magnet because they are opposite side to the electron. You can't do that with permanent magnets, so the program 11 GeV positron with possibly using the new detectors too, right? I mean, there are proposals where we're going to use SOLID, but for the electron, that will be only the electrons that go to 22 at the moment. Right. Question?
Hello?
Yeah.
When they're measuring the quantum efficiency of the beam, what is it that they're measuring?
So in the injector, we are measuring the quantum efficiency of the cathode, indeed, because so what that is as you put lasers on your cathode, you extract, you know, electrons from it with at a certain efficiency, which is called the quantum efficiency, and this degrades as you pull more and more electron. And one of the challenge for this machine, and in particular for the positron machine, will be to be able to make injector guns that have high lifetime, meaning the quantum efficiency is staying high for a long time. Otherwise, you have to stop delivering physics after a few days and reactivate your cathode. So that's one of the issues. If that's what you meant, the quantum efficiency, it's the gun. Yes, we measure it regularly.
Thank you.
Hi. Hello.
Yes.
Yeah. So could you please talk a bit more about the relation between the polarization of the laser and the polarization of the ejected electron?
Yeah. So in general, the way this works is, again, if you have circularly polarized electron, by conservation of velocity, you can show that the electrons that you produce in that reaction is going to carry longitudinal polarization. But that's not the entire story. After you've got that longitudinally polarized electron, it can be in orientation longitudinally. You have to transport it, right, and keep that preferential direction. Most experiments, they want the beam to arrive longitudinally polarized, either along the beam or 180 from it. Some experiment want transverse because some of the physics you measure needs a transversely polarized beam. So transverse to the beam is in or out of plane. We can do all those combinations. The way we do that is is, so if you don't do anything first, if you don't do anything and you have a longitudinally polarized electron and you send it through the accelerator, what happens? Well, it processes Larmor precession. Each time it goes through an horizontally bending dipole, which has a field like that, it will process around it. And by the time you get to the hole, it will have processed thousands of times. And it may not be oriented like you want. So what we have things I didn't mention in the injector, Vin filters. We have device allowing us to orient the polarization vector any which way, even 3D. So we calculate ahead of time where we will land in the hole in terms of the orientation, and then we preload the thing by adjusting the Vin filter at the start of the machine, so that by the time you get to the hole, it's perfectly aligned. This depends, of course, on acceleration, obviously, the precession. So we calculate all of that, taking into account the acceleration. This means that when you have more than one hole that requires polarization, we have energies that are such that you can produce maximum polarization in two holes. If not, you adjust the Vin filter and you share the polarization. But you optimize all of that, and that's part of the optimization we do when we do the scheduling, okay? Not just the current or the path, like I was telling you earlier, but more importantly, can we deliver the polarized beam to those two holes as they require maximum polarization? Most cross sections are directly proportional to that, right? So you want high polarization. And we do that by manipulating the polarization of the beam with the Vin filter and also the acceleration. So that's how this is accomplished. It's measured, by the way, in the holes, because we can calculate it pretty accurately within a degree or two. Holes have spectrometers, Canton or Moller in hole A and hole C, and they measure the polarization in the hole when they're about to do the experiment, and they let us know, accelerator, okay, guys, you're off by 3 degrees, and we optimize it, right? You can actually also use that to measure the energy really accurately at 5 pass, because there's so many precession that being off just by a degree it doesn't require much energy error, and so you can use that to measure the energy.
Thank you. Can I ask another question?
Of course.
So my next question is related to the beam structure that you talk about. So
Yeah.
and that question contains 2 parts to it. So is the beam profile that we're talking about Gaussian, or is it something else?
Yes. So it's electron. Electrons, they emit radiation, which is great because, well, it's great and bad, but it's great because this means that they reach an equilibrium, which means most of the beam distribution, unlike a proton machine, they are Gaussian. Yes, that's absolutely. Unless you're scraping somewhere or you have issues of beam formation, and then you have tails and stuff. But in general, yes, the beams are Gaussian. You can assume that it's a Gaussian beam with a pretty good accuracy.
All right. And so like when we use that beam profile in the halls, is there a particular advantage of using a Gaussian beam, or?
Well, it's just the way it comes out, right? When you produce, when you accelerate, and because of synchronization, and when you accelerate the beam, the distribution will converge to a Gaussian. So that's what you end up with. It's like Poisson distribution going to Gaussian if you have enough, right? That's what's going on there, right? So the beam is Gaussian. Now there are machines for which that's not the case, but this is not the case for high charge, for example, high burn charge, but that's not the case here at CEBAF. So we have a Gaussian beam. So that makes it easy also for experiments because we have device to measure the beam sigma. And so you can say, okay, 3 sigma of the beam is most of my extent, 95% or whatever, right? In hole B, for example, they measure the halo that way, and they usually want, no halo up to 6 or 7 sigma. And their device are accurate enough to measure 6 sigma, to measure the beam halo out 6 sigma, right?
Just the last question, and it's yeah. So you mentioned that because of the Lorentz boost, the transverse direction gets squeezed.
Yeah. PT, right? P transverse angle. So each electron in the bunch, they have their own longitudinal momentum and transverse momentum, mostly longitudinal because they are going forward, right? But there is a phase space, right? The phase space is position and angle. Angle is like px over p total or py over p total and so on. So that's what, and when you accelerate, the px, the transverse will shrink. You can see that from the Lorentz transformation. And so you will end up with smaller beam.
Thank you.
Okay, I think we can go for the break now. If you have more questions, please feel free to go to Yves and have a coffee while asking questions. And we get back in 15 minutes for the next lecture. Thank you.